In this video, we'll talk about how to calculate the area of a surface of revolution. Alright, so there's two main kinds of surfaces we have in mind. The one on the left, the one on the right here, either from revolving around the y-axis like so, or from revolving around the x-axis like that. These are relatively simple three-dimensional shapes. They have a certain regularity to them, which is going to allow us to use one-dimensional calculus to calculate certain aspects of these three-dimensional problems. So here's the idea. The idea is you can slice such an area up into a bunch of bands, and to calculate the area of any little band, you just take ds, the little arc length along there, and multiply by the circumference. So the circumference here, since the radius is x, is 2 pi x. So the dA for this little band is 2 pi x dx. In contrast, over here, the radius for the band is y. So we do 2 pi y ds. Alright. Now ds is the arc length, which we have talked about in our previous video. And, the ds we can get from, well, either looking at dx dy squared plus 1 or dy dx squared plus 1. This was what we talked about in the previous video, right? This is just the arc length. We integrated this to get arc length. This is a little bit new. If we did think of x as being a function of y, then we could calculate dx dy like so, and that would be the formula for ds. So either to calculate the area of the surface revolution, we're going to do this integral. If we're thinking about, again, a revolution around the y-axis, something like that. On the other hand, to add up all the dAs for a rotation around the x-axis would be like this: 2 pi f of x square root of 1 plus df dx squared. This is because f of x is equal to y. That's my radius. Over here, x was equal to g of y. That's my radius. But in both cases, the principle here is the same. We just sum up all the little areas of each band, and the net area is what we call surface area. Right? All right. Now, another remark. The idea of finding dA for an infinitesimal band, then using integration to calculate a from the integral of dA, is yet another example of the infinitesimal method. This heuristic principle is a shorthand for writing a finite approximation model for the application, then passing to the limit to identify the finite sum, transmogrifying into an integral, a definite integral. I said that's not a word, but I wrote it. You understood it, so I don't know. It's up for debate. I think Calvin and or Hobbes would agree with me here. Moving on. Example 1. Again, a somewhat famous example. Calculate the surface area formed by rotating this curve, y equals the square root of r squared minus x squared, from 0 to r, about the x-axis. Alright, so let's get to it. Now what we're doing actually now is we're calculating the surface area of a sphere, because this is a circle, the upper half of a circle. If you take the upper half of a circle and you rotate it around, well, it's a hemisphere. It's just this curve rotated around. It gives me half the sphere, surface area of half the sphere. All right, so getting back to the calculation, dy dx is 1 over twice the square root. Then I have to multiply by the derivative of the inside function, which in this case gives me minus 2x. The 2's cancel. I get minus x over the square root, r squared minus x squared. Therefore, 1 plus dy dx squared is equal to this. Making a common denominator, we end up canceling the x squareds, and we get that. This is very, very familiar to the arc length calculation we did for the circle. In fact, this is a lot of the same algebra, isn't it? But the difference here is that when we calculate this formula, this and that cancel. Again, so here, to be fussy, perhaps this is still an improper integral, but I won't tell anybody if you don't tell anybody. So these cancel, and we have the square root of r squared, which is r. All right. And so we get 2 pi r dx, and So, I mean, I was joking a little bit, but if we did, I mean, I guess technically speaking, this is an improper integral. We should approach r with a limit from the left, but that calculation would be not that interesting in some sense because we still, inside the limit, have this calculation. Anyway, let me shut up about that. All right, so we have this simplifies back to integral from 0 to r of r dx. Now that is definitely not improper, right? And so integral of r dx from 0 to r just gives me an r, so we get, oh, excuse me, it gives me r times r, r squared. So 2 pi r squared, which of course is half of the surface area of a sphere, double that up, and you get 4 pi r squared is the surface area of a sphere of radius r. I'm going to move on before I say some other stupid joke here. All right, moving along. Get out of here. Get out of here. All right. Forgetting where the... There we go. So we're supposed to find the surface area formed by rotating y equals x squared from 0 to 1 about the x-axis and then about the y-axis. We're just going to set up the integrals this time. So, great. Here it is. A, about the x-axis. So about the x-axis, I've got y equals x squared, dy dx is 2x, so I have to do 2 pi x squared square root of 1 plus 4x squared dx, and there you go. Now, about the other axis, we have to think about it. X is going from... well, y is going from what to what? Y is also going from 0 to 1. 0 is less than y. That's an accident here. Generally speaking, the x bounds and the y bounds don't have to agree. So when you think through it, you got to think about, well, what range does my curve go over in the y? But here, y and x both go from 0 to 1, so it's a coincidence, but you know, the integral from y is going to go from 0 to 1. Now, of course, x is going to be equal to plus or minus the square root of y, if we solve that. But since x is positive, we choose the positive square root. And dx dy is 1 over 2 root y, which means that 1 plus dx dy squared is 1 plus 1 over 2y. Thus, here's the integral. Integral from 0 to 1, 2 pi square root of y, square root of 1 plus 1 over 2y dy. This is the arc length calculated in terms of, well, excuse me, these are different surfaces, right? The one was for rotating about the x-axis, the other one was rotating about the y-axis. These would actually be different surfaces, and these would be different, the area of those different surfaces. In some sense, I shouldn't use A for both of them, right? I mean, this A and that A are not the same A, so that's bad notation on my part. Example 3. We'll actually do the calculation. And this one's got some calculation to it. Let's see here. So here we're going to find the surface area of y equals the square root of 1 plus e to the x between 0 and 1, revolved around the x-axis. Find the surface area. All right, so we go to town here. dy dx is that. Square it, we get that. The e to the x upstairs, guys, is the chain rule, right? The outside function square root, so I get 1 over 2 square root. Derivative inside function gives me e to the x. When I square this, I get e to the x quantity squared, which is e to the 2x. The half squares to a fourth, and the square root goes away. And so there you have it. The area, surface area, 2 pi square root of y, 2 pi y, which in this case is square root of 1 plus e to the x, square root of 1 plus dy dx squared, which is that. Then, how on earth am I supposed to integrate that? Well, let's look at it. So my first move was to use properties of square roots. So the square root times the square root is square root of products. All right. Then I multiply that through. That gave me 1 plus e to the x, and then this and that cancel, which gives me 1 plus e to the x plus 1/4 e to the 2x. All right. Getting somewhere. We're getting somewhere. Now that, if you tilt your head and squint, can see is that's 1/4 e to the 2x plus C4. You didn't realize it, but that's actually 4 over 4 times e to the x. So you see that. So I factor out a 4, 1/4, where there was a 1 before. That puts a 4 here, right? Listen, if we multiply this out, we get back to there, which shows you that my algebra is right? So 1/4 e to the 2x, 4 times 1. 1/4 times 4 gives me e to the x. 1/4 times 4 gives me 1. So there you go. Now the reason I did that was to emphasize, just to make the arithmetic a little bit easier. You hopefully can see that this is actually e to the x plus 2 quantity squared. And there's still this 4th, right, which I actually pulled outside and made that 2 vanish because the square root of 1/4 is 1/2, and 1/2 times 2 is just 1. So there you go, 0 to 1, pi, that. Oh, well, isn't that convenient? The square root of something squared is just that. And then I integrate, evaluate, and answer. Pi times e plus 1. So it was kind of scary at the start, but if we just do the algebra, we could figure it out. Now, as I warned you back with arc length, you know, outside of textbooks, if you just try to calculate the surface area of graphs, you're more than likely going to need a numerical method. But, you know, again, textbooks give you problems that are partly intended to hone your algebra skill, which is important, not so much because you find yourself doing algebra all the time, but honing algebra skill, getting good at algebra, being able to see past equations allows you to understand and analyze, speak the language of mathematics. Right? You don't want to be tired just thinking through the language as you go on to higher courses, right? You want the math to be second nature to you so that you can focus on the new applications, and that's what we're trying to get you to. In these calculus courses, we're trying to get you to be able to think in mathematics, to be comfortable. Anyway, moving on. Y equals 1/3 x to the 3/2. We're going to find the surface area formed by rotating this about the y-axis. Alright, so in order to do that, I need to find x as a function of y. So let's see here. I gotta solve for x, basically, is the point. So solving for x, I get 3y is x to, I'm not there yet. 3y is x to the 3/2. Take the 2/3 power both sides here. I get x is y, 3y to the 2/3. Then I differentiate it because I'm, you know, when I know where I'm going. I get 2 over, I can't even read that. The cube root of 3y was y to the minus 1/3, right? Now when x equals to 0, we get y equals to 0. And when x is equal to 12, we get y is, what is it? Well, y is 1/3 of 12 to the 3/2, which is 8√3. This one's more exciting. We actually get really different bounds. When we convert the x bounds to y bounds for the curve, they're really quite different, right? And so there it is. Integral from 0 to 8√3, that's what the curve goes over as we look at y. And 2 pi x, but x is, again, 3y to the 2/3. Square root of 1 plus y, I said the square root of dx to y squared plus 1, which is this. And I chose to use a computer algebra system to integrate here. I'll do the next one directly. Actually, I think I do this one directly on the next page, but for the sake of this page, I just used a computer algebra system to integrate this thing. And when I did, it gave me this lovely number, which simplifies to that 3,712 pi over 15, which is approximately 777.44. So there you go, the surface area, this thing is that. Now, then I took my medicine and I calculated the integral directly as opposed to using computer to do it. Here it is in all of its glory. So to calculate that integral directly, we can do it. It's not impossible, just requires some tinkering. So my opening move was to factor out y to the 2/3, like so. And then I brought that outside the square root. They gave me y to the 1/3. And then this. I said, okay, well, I'm going to let that equal to w. That gave me a dw, which gave me a dy, which was y to the 1/3 dw. Excuse me. And then I plug that in. I got y to the 1/3, y to the 1/3, square root of w, 3/2 dw. Now this times that gives me y to the 2/3, right? Which I can trade for w. Well, not quite w. Actually, y to the 2/3 is w minus, let me scroll up a bit here, y to the 2/3 is w minus 4 over 3 to the 2/3 because that. And so this becomes that and that. And at this point I've just got, something I can straight integrate in w because that's just 3/2. W to the 3/2, w times w to the half is w 3/2, minus 2 third root of 3w, square root of w like that. These I can both integrate as I do, and that gives me this. And then, anyway, there you go, antiderivative. And then you can plug numbers in, but yeah. I don't know. So it depends on what you're after and what you're asked. It's important to know that we can do integrals numerically. In fact, perhaps you should take a course which is solely focused on numerical methods at some point. We do offer a course residentially called Math 352, which is almost entirely focused on how to calculate things with numbers up to whatever precision you want. I think we discuss integration in there, but also more interesting things like differential equations and other things. But anyway, that's it for this video. Thanks.